Ooh, I'm washed out. Okay. So we're doing the product rule today. The short story about the product rule is when you take the derivative of the product of two functions, here symbolized by f at x and g at x, the derivative of the product can be found with the following song. Derivative of the first times the second plus the first times the derivative of the second. It's kind of a nice song. Anyways, first thing we're going to do, one of the things I will probably ask you to do on a test is reproduce the proof of the product rule. We're through the looking glass here. You're not supposed to do this in Ontario, but we'll do it. Just because we are that good. Okay. So I have two functions, f and g. They're differentiable everywhere. And I am going to take the derivative of the product of those two functions. So the derivative of f at x times g at x. And in order to do that, well, I'm going to use the difference quotient. So I'm going to take the limit as h goes to 0 of f at x plus h times g at x plus h minus f at x times g at x. And I'm going to take my ruler and be uncharacteristically neat, and I'm going to underline that. I'm going to put an h there. Okay. So there's the difference quotient set up for the product of those two functions. And if I start putting h in, I basically can't do anything, and you would find that you can't manipulate this in the way, in the form that it's in. And so basically, this proof involves a little bit of algebraic trickery. So f at x plus h times g at x plus h. Now this looks an awful lot like f at x plus h minus f at x, which is just the original plain ordinary difference quotient. So I'm just going to willy-nilly put plus f at x into that. Minus f at x. And I can't just willy-nilly do that. So I'm going to have to add f at x back in over here. And just be patient with me till I get to the end here. And I'm going to subtract f at x times g at x out here at the end. Okay. Now, this is a subtracting g at x. So it'd be really nice if we had like g at x plus h in this position. Okay, so I'm just going to put it there. And I can't just willy-nilly throw a g at x plus h into this expression, so I have to put it in both places. Okay. So what you will notice, I've just gone from this step. Wow, this really goes up on a hill. To this step. I have subtracted out f at x times g at x plus h, and then in order to keep the expression the same, I've added it back in, and then I've continued with my difference quotient, and this underline is just going to point out how crooked I've made this. This whole entire thing is over h. Okay. Whoa. If I look at this, these two expressions, these are starting to look like the difference quotient with the g at x plus h intermingled. This is looking like the difference quotient for g at x with an f at x intermingled. So here we go. Let's start to tease these apart. Limit as h goes to 0. I don't like you, g at x plus h in these two terms. And so I'm going to factor a g at x plus h out. And this is f at x plus h minus f at x. Ooh, this is looking better already. Okay. And I'm going to break these into two fractions. And so it's just the opposite of adding them. I have a common denominator. I'm going to go back and take them apart. Right. There we go. Look, that looks so much like the derivative of f at x. And let's see, if I take f at x out of this one, I wind up with what looks like and is the derivative of g at x. I better put big curly brackets around put square brackets around rather than braces. Okay. Just to indicate that the limit applies to everything in there. All right. So now, the limit of a product is the product of limits. So this is limit as h goes to 0 of g at x plus h times the limit as h goes to 0 of f at x plus h minus f at x all over h. And this is limit as h goes to 0 of f at x times the limit as h goes to 0 of g at x plus h minus g at x, and that's all over h. Look, I think it's safe. Children, we've made a safe place in the earth. We can now put our limits into this. So the limit of h as h goes to 0 of g at x plus h is g at x. And the limit as h goes to 0 of this is the derivative of the first function. And the limit of as h goes to 0 of f at x is just f at x. And the limit as h goes to 0 of this expression is g primed at x. And that is the proof of the product rule. Okay, so there's this little bit of magic that goes on here where we subtract something out and add it back in. And then the rest of it is just basically straightforward algebra. And it winds us up, it ends us up with the product rule down at the bottom. Okay, so let's apply the product rule. So whenever we have two functions multiplied together, we can use the product rule. When we have a rational function, we can use a little bit of magic and use the product rule, or we can use a thing called the quotient rule. And we'll actually do the quotient rule not tomorrow, but the day after tomorrow. Okay, so let's find the derivative with respect to x of x cubed plus 2x plus 1 times x squared plus 3. Okay, I know what you're thinking. You're thinking, I could just expand these and take the derivative, and that would be a lot easier. But we've grown up now. We're going to use the product rule. So I noticed that this is my first function, this is my second function, and so I'm literally going to make a little space here. I'm going to say that f at x is x cubed plus 2x plus 1. And because I know I need to know the derivative, I'm just going to write that right away. So it's 3x squared plus 2. G at x, my second function, I'm going to write it here, x squared plus 3. And so g primed at x is 2x. Okay, so there. I've separated out my two functions. I've found their derivatives. I know that the derivative of this is just going to be using my product rule. And so let's write this out. The derivative of f at x times g at x is equal to first times the derivative of the second plus the derivative of the first times the second. You will notice that you can add these in any order. You can multiply these in any order. Won't matter. So let's do this. F at x is x cubed plus 2x plus 1. And the derivative g primed at x is 2x. And then the derivative of x, sorry, the derivative of f at x is 3x squared plus 2. And then the derivative, or sorry, the original function g at x is x squared plus 3. Okay. And at this point, we actually just leave it alone. Rather than expanding it and collecting like terms, we will just leave it alone. You will find you might be asked to find the slope of the tangent at that point, at some point, in which case you just substitute that point into that expression and do the math. Okay, let's do a slightly more complicated one. But not that much more complicated. So let's do the derivative of the cube root of x times 7x cubed minus 2x plus 1. So we're taking the derivative with respect to x of that expression. And so f at x, I'm just going to write as x to the exponent 1/3 because that little 3 inside the caret of the surd, they are called surds, means cubed root or to the x to the exponent 1/3. I take my derivative using my power rule because I can do that. Subtract 1 from the exponent, I get negative 2/3. Okay, my second function, g at x, is 7x cubed minus 2x plus 1. So g prime at x is 21x squared minus 2. I'm all ready to go into finding my derivative. And so this is just going to be equal to, once again, let's just do it up here. So first, times the derivative of the second, so x to the exponent 1/3 times the derivative of the second, 21x squared minus 2 plus the second function. So, or sorry, let's do the derivative of the first. So 1/3 x to the exponent negative 2/3. Derivative of the second times the first, 7x cubed minus 2x plus 1. We could tidy it up a little bit if you like the radical notation. We can just put that in. And at this point, we aren't actually going to do any expansion or simplification. All right, so there we go. So we've had 2 examples of using the product rule. I super recommend making this little parking lot here, picking out the 2 functions, writing the function and its derivative, and then just plugging it in up there. And you can do that. You can do that at, any way you want. All right. Next thing we are going to look at is a pattern for the derivative of 3 functions multiplied together. So we're just going to use the product rule, and then we're going to use the product rule again. Okay, so we have 3 functions, f at x, g at x, and h at x. So just notice they're all functions of x because I'm going to simplify them a little bit for the purposes of showing this, showing the pattern of the derivative of the product of 3 functions. So these are all differentiable in the neighborhood we're interested in. They're all functions of x, and we're just going to use f, g, and h to represent them. So we're just going to represent those super easy. They're all functions of x. And our problem is find the derivative with respect to x, and they're functions of x, of f times g times h. So I've just left out the brackets and the x's because it gets a little exhausting to write out all the brackets and the x's and makes it just a little too busy to appreciate the beauty of the math. Okay, here's our secret. We just treat g times h like the second function and see what we get. So first times the derivative of And I said g plus h, didn't I? G times h plus the derivative of the first times g times h. All right, did I really want to do it that way? I didn't, but that's okay. It's not going to come out in the order that I wanted, but that's all right. We can rearrange it. Okay, now we need to do the derivative of g times h. We're just going to apply the product rule here. Okay, so derivative of, oh, sorry. There is no primed there. Sorry, everybody. Derivative of the first function times the derivative of the second plus the second function times the derivative of the first plus f primed times g times h. And I can expand this. This is f times g times h primed plus h times g primed times f plus f primed times g times h, which I could rearrange just to make it tidy. F primed times g times h plus f times g primed times h plus f times g times h primed. Okay, so notice the pattern that we've got. Once we rearrange it, we just are adding those three expressions, and the derivative is just jumping between each expression. And that would work if we did the product of four expressions. It would look very much the same. Anyway, there's the derivative for the product of three expressions. Last thing we will look at is what is the derivative of the power of a function. Be ready, derivative of the power of a function. And so I'm just going to take what I have here, and instead of f times g times h, we're going to do f times f times f, which, by the way, is f at x to the power of 3. So in other words, we're really finding the derivative of f at x cubed. Okay, so I'm just going to take this derivative of the product of three functions, and I'm just going to start throwing f's everywhere, even where I see g's and h's. Okay, so this becomes f prime times f times f plus f times f prime times f plus f times f times f primed. That's a lot of f's.
So is it just f squared, 3f squared f prime?
3 times f, oh, I can just put this, 3 f squared times f primed. Or in other words, it's 3 f at x squared times the derivative of f. Okay? And if we did the next product, if it was f to the exponent 4, it would be 4 f to the exponent 3 times the derivative of whatever f is.
So it is like the power.
It's exactly like the power rule, but we just have to take into account the fact that we have a function on the inside. And we do that by taking the derivative of the inside function and multiplying it by that power rule result.
So does this get into like a chain rule now?
So does it?
A function on the inside and then you're cubing it?
Yes. So this is just like the chain rule. Okay. So let's find the derivative with respect to x of x squared plus 3x plus 1 And let's raise this to the power of 3. Okay, so this is, I'm going to say f at x is x squared plus 3x plus 1. The derivative of f is 2x plus 3. And so just remembering that the derivative of f at x cubed is equal to 3 times f at x squared times the derivative of f at x. So that was just my power rule from before. This means the derivative of x squared plus 3x plus 1 cubed is 3 times x squared plus 3x plus 1 squared, and then times the derivative of f at x, which is 2x plus 3. Okay, so we've gone a little further than normal. So we've done proof of the product rule. Okay, so that'll be on a test. We've done a couple of examples of product rule. We've done the derivative of the product of 3 functions and looked at that pattern. And then we've extended it out to do the derivative of the power of a function. And that's the product rule. Any questions?